this is chapter 9, you're probably already familiar with functions that look like y equals x to some power. For example, y equals x squared. And so we call these power functions, where y is equal to x, which is the base, to some power. And so the base is the variable. And so, for example, let's look at y equals x squared. We have values for x. We have the function of x, which is x squared, and then we have values for y. And so let's plug in some numbers here. Let's say that x is 3. It can be 2. It can be 1. It can be 0. It can be -1, -2, or -3. And so the function will be x, which is 3, squared. Oops, I'm sorry. How about 3 squared? Or 2 squared? Or 1 squared? Or 0 squared? Or -1 squared? In parentheses. Or -2 squared? Or -3 squared? And so 3 squared is 9. 2 squared is 4. 1 squared is 1. 0 squared is 0. -1 squared, which means -1 times -1 is +1. -2 squared, which means -2 times -2 is +4. And -3 squared is +9. And so we can graph this function. And so x can either be 0, or 1, or 2, or 3, or -1, or -2, or -3. And when x was 3, y was 9. So let's see, how about 1, 2, 3, 4, 5, 6, 7, 8, 9. When x was 3, y was 9. When x was 2, y was 4. When x was 1, y was 1. When x is 0, y is 0. When x was -1, y was +1. When x was -2, y was 4. And when x was -3, y was +9. And so we get this function. You're probably familiar with this. This is the function y equals x squared. This is a parabola. And so again, we call this the power function. And what we want to consider now are functions that don't follow the form of y equals x to some power, where the power is a constant, right? The power was always 2, and the base was changing. But instead, we want to consider functions that follow the form of y equals b to the x power, where the base is a constant number and it's the exponent that can change. And so we need to set some stipulations here. First of all, b has to be greater than 0. So b cannot be 0 or a negative number. And also b cannot be equal to 1. B could be a decimal. It could be 0 point something, but it can't be 1. And the reason for that is because 1 to any power is always 1. So even though the exponent is changing, if the base was 1, that wouldn't change the y values as the x values changed. This is example 1. It says graph y equals 2 to the x power by plotting points. And so what they want us to do is same thing we did just a second ago, which is to say that we have some values for x, we have a function of x, and we have some values for y. And so let's let x be equal to 3, 2, 1, and 0, and -1, and -2, and -3. And so the function of x, if x is 3, we'll have 2 to the third power. If x is 2, we'll have 2 squared. If x is 1, we'll have 2 to the first. If x is 0, we'll have 2 to the 0, 2 to the -1, 2 to the -2, and 2 to the -3. And so here the base is always a constant. It's always 2, but it's the exponent that's changing. And so y will be equal to 2 to the third, and I'm going to go ahead and write this out as 2 times 2 times 2, which is equal to 8. When x is 2, y will be equal to 2 times 2, which is equal to 4. And when x is 1, we will have just 2, which is 2. And when x is 0, we're going to have 1. And so let's see why that is. Well, if 2 to the third is 2 times 2 times 2, which is 8, it wouldn't make any difference if I put 1 times 2 times 2 times 2. I would still get 8. And it wouldn't make any difference if I put 1 times here. 1 times 2 times 2 is still 4. 1 times 2 is still 2. And 1 is just equal to 1. And so look at the pattern. Here I had 1 times 3 2's, 1 times 2 2's, 1 times 1 2, and then 1 times no 2's, right, which is just 1. And you can also see the pattern in the results. We have 8, 4, 2, 1. And so the pattern is 8 divided by 2 is 4, 4 divided by 2 is 2, and 2 divided by 2 is 1. And so if we continue this pattern on, 2 to the negative 1 power must be 1 half, because 1 divided by 2 is 1 half. And 2 to the negative 2 power is going to be 1/4, because again 1 half divided by 2 is 1/4. And 2 to the negative third must be 1/8. Again, just following the pattern. So again, 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, divided by 2 is 1 half, divided by 2 is 1/4, and divided by 2 is 1/8. And so these are our x, y points that we want to plot. And so let's look at a graph. We have the y-axis and the x-axis. And the values we're plugging in for x are -3, -2, -1, and 0, and 1, 2, and 3. -3, -2, -1, 0, 1, 2, and 3. And so when we plugged in 3, we had a value of 8. 1, 2, 3, 4, 5, 6, 7, 8. Had a value of 8 when we plugged in 3 for x. When we plugged in 2 for x, we had 4 for y. We plugged in 1 for x, we had 2 for y. When we plugged in 0 for x, we had 1 for y. We plugged in -1 for x, we had 1 half, which would be about here somewhere. We plugged in -2, we had 1/4, which would be about here somewhere. When we plugged in -3, we had 1/8, which is about here somewhere. And so we get a function that looks something like this. And so we call this the exponential function. And this is what an exponential function looks like when graphed out. So in general, we can say that for exponential functions that look like y equals b to the x, that if b is greater than 1, generally we are going to have an increasing exponential function. This will be an increasing exponential function, meaning that as x increases, so does y. And so this graph has a positive slope all throughout the graph. As x gets bigger, so does y. This is example 2. It says graph y equals 1/2 to the x power. And again, they want us to do this by plotting points. And so we'll do the same thing again. We'll have values for x, we'll have a function of x, and we will have values for y. X can be -3, -2, -1, 0, 1, 2, and 3. And so the function will be when x is -3, we will have 1/2 to the -3rd power. We will have 1/2 to the -2 power. We'll have 1/2 to the -1 power. 1/2 to the 0 power. 1/2 to the first power. 1/2 squared. And 1/2 to the third. And so let me start down here. 1/2 to the third power. That means 1/2 times 1/2 times 1/2. And so when we multiply fractions, we just multiply the numerators together. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. And so when x is 2, we'll have 1/2 times 1/2. Same thing, 1 times 1 is 1. 2 times 2 is 4. 1/2 to the first power is just 1/2, which is 1/2. 1/2 to the 0 power is going to be 1. And in fact, we'll see that any number raised to the 0 power is always going to be 1. And so we're kind of following a similar pattern here. The pattern is if we take 1/2, 1/8, and we multiply by 2, we get 1/4. 1/4 times 2 is 1/2. 1/2 times 2 is 1. And we can just continue that pattern on from here. 1/2 to the -1 power is going to be 2. 1/2 to the negative 2 power will be 4, and 1/2 to the negative 3rd power will be 8. And so in general, we can say that any number raised to a negative exponent, let me say that any number raised to a negative exponent is the same as 1 divided by that same number to a positive exponent. And so, for example, when we have 1/2 to the negative 3rd power, that is the same thing as 1 over 1/2 to the positive 3rd power. And so that means we have 1 over 1/2 times 1/2 times 1/2, which is 1 over 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. And so we have 1 divided by 1/8. And when we divide fractions, 1 divided by 1/8 is the same thing as 1 times 8 over 1, right? So when we divide by a fraction, we multiply by the reciprocal, which is just 8. And so that's why we're getting 8 for y here. And again, you can see the pattern that was formed, very similar to what we saw in the last example. 8 divided by 2 is 4. 4 divided by 2 is 2. Divided by 2 is 1. Divided by 2 is 1/2. Divided by 2 is 1/4. Divided by 2 again is 1/8. So we'll graph the equation. And we have x values that are -3, -2, -1, 1, 2, and 3. And our y values will go all the way up to 8. 1, 2, 3, 4, 5, 6, 7, 8. And so when we plugged in -3 for x, we got 8 for y, so up here. When we plugged in -2 for x, we had 4 for y, so about here. Plugged in -1, we got 2 for y. Plugged in 0 for x, we got 1 for y. Plugged in 1, we got 1/2. Plugged in 2, we got 1/4. And we plugged in 3, we got 1/8. And so we get a function that looks something like this. And so in general, again, we can say that if b is greater than 0, but less than 1, and so b in this example is the base, 1/2, right? So we're saying that b is a fraction. It's less than 1, but it's greater than 0. If that is the case, we will have a decreasing function, meaning that as the x values get bigger, the y values get smaller. And while we're here, I should also point out that no matter how big x gets, the y value will never be negative. It just gets closer and closer to 0 as we go out to infinity. So as x gets really, really big, y just gets really, really small. And as x gets really, really small, y gets really, really big. Example 3 says graph y equals 3 to the negative x. And again, they want us to do this by plotting points. So we'll do the same thing. We have x, we have a function of x, and we have y. And so we'll let x be equal to 3, 2, 1, 0, -1, -2, and -3. And the function will be 3 to the negative x. So if x is 3, then negative x is -3. This will be 3 to the -3 power. This will be 3 to the -2 power, right? If x is 2, negative x will be -2. 3 to the -1, again because if x is 1, negative x is -1. This would be 3 to the 0, so 0 can't be negative. We don't need to put a negative in front of 0. If x is -1, then negative x must be +1. If x is -2, negative x will be +2. And if x is -3, negative x will be +3. And so we'll start down here. This is the easier one. 3 to the 3rd power means 3 times 3 times 3, which is 27. 3 squared is 9. 3 to the 1st is 3. 3 to the 0 is 1. Any number to the 0 power is 1. And again, you can see the pattern. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. 1 divided by 3 will be 1/3. 1/3 divided by 3 will be 1/9. And 1/9 divided by 3 will be 1/27. And so we can plot this function. our x values would be -3, -2, -1, 1, 2, and 3. And so when x is -3, y is 27. And so we need 27 marks here. Hopefully I'd be okay if I just estimate. Maybe 27's up here somewhere. So when x is -3, y is 27. When x is -2, y will be 9, which is about a third of that, maybe about here. When x is -1, y is 3, which is about a third of that. When x is 0, y is 1, about a third of that. When x is 1, y is 1/3. When x is 2, y is 1/9. And when x is 3, y is 1/27. So again, we get something that looks like this. This will be our exponential function, y equals 3 to the negative x power. The book asks the question, what does the graph of y equals 1/3 to the positive x power? What does this graph look like? And well, the answer is it's exactly the same. So remember that if y is equal to 3 to the negative x power, when the exponent is negative, this is the same thing as 1 over 3 to the positive x power. So anytime you have a negative exponent, you can put the base and that exponent in the denominator and change the sign of the exponent. And 1/3 to the x power means 1 to the x power over 3 to the x power. So that's one of the rules of exponents. When you have a fraction raised to an exponent, you're raising the numerator and the denominator to that power. And so 1 to any power is just 1. It doesn't matter what x is. And 3 to the x is 3 to the x. So you can see that 1/3 to the x power is exactly the same as 3 to the negative x. So we've already graphed y equals 3 to the negative x. We're going to get the exact same answers if we try 1/3 to the x power. They'll be exactly the same graph. Example 4 says find 2.5 to the 1.4 power, and also find 150 to the 2/3 power. And so if the base and or the exponent is either a decimal or a fraction, this is not as easy to figure out on paper, right? So we need to use our calculator for this. It'll be a lot easier that way. And so it depends on the calculator that you have. You're either going to type in 2.5, and you might have a button that looks like this, like a caret. And you'll type in 2.5, the caret button, 1.4, and then you'll press equals. And again, depending on your calculator, you may have a button that says y to the x power, or x to the y power, and then 1.4. These two buttons mean the exact same thing. It just depends on the calculator that you have. And then you'll press equals. With this one, we want to type in 150, and again, we'll use either the caret button or the y to the x button. But we want to make sure that we type in parentheses first, right? So your calculator probably has an open parenthesis button. You want to type in 2 divided by 3 to give us 2/3 as the fraction, and close parentheses, and then press equals. And so it's really important here to make sure that this exponent being a fraction, in your calculator you put that in parentheses. Otherwise your calculator may think that you want 150 just to the second power, and then whatever that answer is, divide by 3, which is not what we want, right? We want 150 raised to this entire power. So make sure that if your exponent is a fraction, you enter that fraction in a set of parentheses. And so let's look and see what we have here. My calculator has a caret button for exponentiation. And so I'm going to type in 2.5, right? My caret button, 1.4, and I'll press equals. And you can see I got 2.5 to the 1.4 power, and the answer is 3.6067, and I'll round it off there. That's good enough. It goes on though 49765. That's close enough. For this one, I want to make sure I type in 150, my caret button, to give me an exponent. I want to have an open parenthesis, 2 divided by 3, and then close parentheses, and then press equals. So you can see my calculator says 150 to the 2/3 power, and this answer will be 20.2311, and I'll round it off about there, about the 4 decimal places. Consider you have a single cell of bacteria. and we'll call this the 0th day. On the 0th day, you have a single cell. And on the first day, right, which is the next day, that single cell has split into 2 cells. So now you have 2 bacteria. On the second day, each of these cells split into 2, and now you have 4. And on the third day, each of these 4 cells has split into 2 again. And now you have 8 cells. And on the 4th day, each of these 8 cells has split into 2. And now you'll have 16. And so this is an example of an exponential function. And so this is following the pattern of 2 to the 0th power, which is just 1 cell. 2 to the first power, which means you have 2 cells. 2 to the second power, which is 4. 2 to the third, which is 8. And then 2 to the fourth, which is 16. And so the exponent here is the day, right? 0, 1, 2, 3, 4 are the exponents. Those represent the number of days that have passed. And these work out to be the number of cells that we have. And so the exponential function in this example is y equals 2 to the x power, where x is the number of days that has passed. And so this is an exponential function, right? The exponent is the variable, the base is a constant. And we'll see lots of different examples of exponential functions. The first one that we're going to look at, other than the basic exponential function, says that y equals a times 1 plus r to the n power. And in this formula, r is the rate of growth. The rate of growth. We want to make sure that that's in a decimal form. So a lot of times it'll be given to us as a percentage. We want to make sure that we express that as a decimal, not a percentage. N, the exponent, is the time interval. Just like in this example, the exponent was the amount of time that has passed. A, in this formula, represents the initial amount. And y is the new amount. Right? That's what we're trying to solve for most of the time. The new amount. Okay. And we'll see here in just a second where this formula comes from and why it looks the way that it does. This is example 5. It says, according to the records of a utility company, the demand for electricity in its area is growing at a constant annual rate of 12%. So we have demand is growing at 12%. During this current year, its customers use 750 billion kilowatt hours, which is 7.5 times 10 to the 11th kilowatt hours of electricity. Assuming no conservation efforts on the part of its customers, how much electrical power is needed in 8 years? So how much power do we need in 8 years if the current demand is 7.5 times 10 to the 11th and we're growing at a rate of 12%? Well, we can use this formula. And I'm going to solve the problem twice, actually, once using the formula and then once calculating the demand for every year in order to see that the formula does in fact give us the correct answer. And so y, that is the power needed in 8 years. That's what we're trying to solve for. A is the initial amount. That's how much we're currently using. So A in this formula is going to be 7.5 times 10 to the 11th kilowatt hours, and then we're going to multiply that by 1 plus the rate. The rate is the rate of growth. It was given to us as a percentage. We need that to be a decimal. To change this to a decimal, we move the decimal point 2 places to the left. So it's going to be 0.12, right? That's 12% as a decimal. And then the exponent n is the amount of time that has passed. That's going to be 8 years. Okay, and so we can work this out. Y is going to equal 7.5 times 10 to the 11th. We're going to go ahead and add these first. It's going to be 1.12. 1 plus 0.12 is 1.12 to the 8th power. And so we'll use a calculator to figure that out. We'll take 7.5 times 10 to the 11th power. and we're going to multiply by 1.12 to the 8th power. Oops, I'm sorry, I made a mistake. See, I typed everything in as an exponent. So let me start over here. I need 7.5 times 10 to the 11th power, and then on my calculator I have to hit the right arrow to come out of the exponent, and then I want to multiply by 1.12 to the 8th power. And we get 1.857, I'm going to round, 1.857 times 10 to the 12th power, and this will be kilowatt hours. So, if our customers do not conserve any energy, they continue to grow at a rate of 12%, in 8 years we're going to need 1.87 times 10 to the 12th, whereas right now we're currently using 7.5 times 10 to the 11th. And so this is 750 billion. This is going to be 1,857 billion. And so you can see it's quite the increase, over double. We need twice as much power in 8 years as we currently have. And so let's think about what this formula means, why this formula gives us the correct answer. So on the 0th year, right, the current year, we are using 7.5 times 10 to the 11th kilowatt hours. On the first year, we're going to increase this by 12%. And so in order to increase this, we need to take 7.5 times 10 to the 8th, that's what we're currently using, 10 to the 11th, that's what we're currently using, plus another 12%. So another 12% is going to be 7.5 times 10 to the 11th times 0.12. Right, that's 12% of our current usage. We're going to add that back into our current usage. And so after the first year, we're going to be using 7.5 times 10 to the 11th power plus another 12% of that. So 7.5 times 10 to the 11th power times 12%. And so after the first year, we need 840 billion, which is times 10 to the 9th. That's going to be the same thing as if the exponent is currently 9, I can move the decimal point 2 places to the left and increase the exponent by 2. Right? That's how the exponential notation here works. The exponent tells me how many times I need to move the decimal point to the right to get the exact number. So 840 times 10 to the 9th means 840 and 9 more zeros. Right? The decimal point is being moved 9 more places to the right. But I want to express this in scientific notation, which is going to be 8.40 times 10 to the 11th. Okay. Now on the second year, we have our current usage, right, which was the previous year, 8.40 times 10 to the 11th, plus I'm going to add in another 12% of what we currently use, right? So we're increasing by 12% each year. So now I'm going to add in another 12% of what I'm already using. So we're already using 8.4 times 10 to the 11th, and I'm going to increase that by 12%, right? 12% of what I'm currently using plus what I'm already using. And so we will be using 8.4 times 10 to the 11th power plus 8.4 times 10 to the 11th power times 12%, right? Our 12% increase. And so on the second year, we're going to be using 940.8 times 10 to the 9th, which again is 9.408 times 10 to the 11th. Now I'm going to continue this on. The third year, we're already using 9.408 times 10 to the 11th power kilowatt hours, plus I'm going to add in another 12%. 9.408 times 10 to the 11th times another 12%, right? So I'm increasing by another 12%. And so on the third year, we're going to use 9.408 times 10 to the 11th plus another 12%. So 12% of that 9.408 times 10 to the 11th, I need 12 more percent of that. And so on the third year, we're going to be using 1.0537, that's good enough, I'm rounding that off, times 10 to the 12th. Right, so now we're using more electricity, right? We continue to increase the amount of electricity that we're using. So I'll stop here, but if I continue this on to the 8th year, we'll see that we get the same answer. And so let's see, where does this formula come from? Why is this giving us the correct answer? You can try this if you like. You can continue this on for 5 more years, and you'll see that you'll get the exact same answer. And so let's look at the first year. The first year, our power used was going to be the initial amount plus the initial amount times the rate. Right? This was our initial amount, 7.5 times 10 to the 11th, that's A, plus A again times 12%. And so in this formula, the A's factor out. Right? We can bring the A outside a set of parentheses, and we'll be left with 1 plus R. And I know that that's correct because if I distribute, A times 1 is A, and A times R is AR. So after the first year, this will be the initial amount. Now on the second year, I'll have this initial amount, A times 1 plus R, and that will be the initial amount for the second year, right, which is what we have here, plus that initial amount again, which is A times 1 plus R, times the rate again, And so here I have a similar situation. The A times 1 plus R is in each term, and that will factor out. And so we'll get y equals the A times 1 plus R. That factors out. And what I'm left with is 1 plus R. Okay, and so I know this is correct because if I take all of this and I distribute it into this set of parentheses, all of this times 1 is A times 1 plus R, and A times 1 plus R times R is A times 1 plus R times R. And so what I'm seeing here is that I have 1 plus R times 1 plus R. That is the same thing as 1 plus R squared. And so at the second year, the exponent becomes 2. At the third year, if I do this again, the exponent will become 3. And at the fourth year, it becomes 4. Fifth year, it's 5, 6, 7, 8. Right? And so that's what the formula says. Whatever the initial amount is, times 1 plus R, to whatever power that we have. And so I'll go ahead and do this for a third year. On the third year, we have the initial amount, which is A times 1 plus R squared, plus I'm going to take the initial amount again and multiply by the rate again. And again, these factor out. These are the exact same. They will factor out. And so when we factor them out, we get A times 1 plus R squared. And what I'm left with when I factor this out is 1 plus R. Oh, I'm sorry, I made a mistake. The square here goes outside the parentheses, right? The square is outside the parentheses. And so I know that this is correct because if I take this and distribute it, A times 1 plus R in parentheses squared times 1 is A times 1 plus R squared, plus all of this times R is plus A times 1 plus R squared times R again. Right, so I know that this is the correct factoring of this equation because if I redistribute it, I get back to where I started. And so here 1 plus R squared times 1 plus R is going to be 1 plus R to the third. And so after the third year, the exponent becomes 3. And again, after the fourth year, it'll be 4. Fifth year, it'll be 5, 6, 7, 8. And so that's where this formula comes from. We can find the current amount by taking the initial amount and multiplying by 1 plus the rate to the nth power, where n is the time interval. In this example, our time interval is measured in years. Example 6 says, Bill and Mary plan to retire this year with a combined annual pension of $60,000. So they're retiring and they're going to get $60,000 per year in their pension. Because of inflation, their purchasing power is constantly decreasing, meaning that their money is worth less and less money every year because things cost more money. So assuming a 7% annual rate of inflation, what will their purchasing power be in 10 years? So if the annual rate of inflation is 7%, that means that their $60,000 will buy 7% less every year, right? Their money is not worth as much. The price of bread and milk and gasoline goes up by roughly 7% every year, right? That's our assumption. And so we use the formula again, which is the exponential growth function for annual increases. And so we're looking for the new amount, and we'll say that their original amount, they're getting $60,000. $60,000 times 1 plus the rate. Now in this example, the rate is 7%. As a decimal, that's going to be 0.07. So again, I move the decimal point 2 places to the left to get 0.07. But that is a decrease in their purchasing power. So this number is actually a negative, right? So we're adding a negative 0.07 in here. We want to find the purchasing power after 10 years. Right, so here their money is worth less money. That's a decreasing rate. We want to make sure that the rate here is a negative. And so their purchasing power after 10 years will be $60,000 times 1 plus a negative 0.07, which is going to be 0.93. So their money is not worth as much as it was. Now it's only worth 93% after the first year. And if we raise this to the 10th power, we will find out what their purchasing power is in 10 years. And so we can do that. We can take $60,000 and we will multiply by 0.93 to the 10th power. And so in 10 years, their money is worth a lot less. Only $29,039. Yeah, $29,039. Right, so this year their money's worth $60,000. Next year it'll be worth a little bit less. Year after that it's worth even less, right? They can't buy as much as they could the year before. And so in 10 years, their $60,000 is going to be equivalent to what only $29,000 is worth this year. They can't buy as much as they could the year before. And so in 10 years, their $60,000 is going to be equivalent to what only $29,000 is worth this year.